Slide 1. Title slide. Thorium in nuclear energy. Slide content. Thorium as next generation nuclear fuel. High energy density power source. A potential safer alternative to uranium. Strategic role in future global energy systems. Thorium represents one of the most strategically significant alternatives to conventional uranium-based nuclear power. Nuclear energy remains the highest density, large-scale energy source available for industrial civilization, and thorium introduces a pathway that potentially reduces long-term waste toxicity, influence fuel efficiency, and enhances safety characteristics. Unlike fossil fuels, nuclear fission doesn't produce carbon emissions during operation, making it central to decarbonization strategies. Thorium-based systems have the potential to reshape the energy economics by offering a stable, long-term supply of reliable power independent of weather conditions, because energy availability determines industrial capacity, geopolitical leverage, and technological progress. Understanding thorium reactors is not simply a scientific exercise but an analysis of future global power structures. Slide 2. What is thorium? Slide content. Chemical element atomic number 90, naturally occurring radioactive material, more abundant than uranium, found in minerals such as monazite. Thorium is a naturally occurring radioactive element discovered in 1828 named after the Norse god Thor. It is classified as an actinide metal and exists primarily as thorium-232, a fertile isotope capable of being converted into fissile fuel through neutron absorption. Thorium is distributed widely across the Earth's crust and is often found in mineral sands containing monazite. Compared to uranium, thorium deposits are geographically diverse, reducing resource concentration risks. The widespread availability of thorium improves long-term fuel security as supply chains become less vulnerable to geopolitical instability. Its physical and nuclear properties make thorium an attractive candidate for advanced reactor designs focused on sustainability and safety. Slide 3. Nuclear energy fundamentals. Slide content. Energy is released from the atomic nucleus. Nuclear fission splits heavy atoms. Chain reaction releases heat. Heat produces steam and electricity. Nuclear energy is generated through the process of nuclear fission, in which heavy atomic nuclei split into smaller. Correction. Nuclear energy is generated through the process of nuclear fission, in which heavy atomic nuclei split into smaller nuclei while releasing large amounts of energy. The energy released originates from the conversion of mass into energy as described by Einstein's mass-energy equivalence equation. Even a small amount of nuclear fuel can produce enormous quantities of thermal energy. In nuclear power plants, this heat is used to convert water into steam, which spins turbines connected to electrical generators. The efficiency of nuclear energy makes it uniquely capable of supplying continuous baseload electricity required for industrial economies. Slide 4. Thorium fuel cycle. Slide content. Thorium-232 absorbs neutrons, converts into pro protactinium-233, decays into uranium-233. Uranium-233 undergoes fission. Uranium itself isn't directly fissile, meaning it cannot sustain a chain reaction on its own. Instead, it acts as a fertile material. When thorium-232 absorbs a neutron, it transforms into thorium-233, which undergoes beta decay into protactinium-233. Protactinium then decays into uranium-233, a fissile isotope capable of sustaining nuclear fission. This conversion process allows thorium to serve as the raw material for nuclear fuel generation. The ability to breed fissile material within nuclear reactor improves through resource efficiency and reduces dependency on enriched uranium supplies. Slide 5. Molten salt reactors. Slide content. Liquid fuel mixed with molten salt operates at atmospheric pressure. Passive safety characteristics, high temperature efficiency. Molten salt reactors represents one of the most promising designs for thorium utilization. Unlike traditional nuclear reactors that rely on solid fuel rods and water coolant, molten salts reactors dissolve under nuclear fuel directly into a liquid salt mixture. The salt acts both as fuel carrier and coolant, enabling efficient heat transfer. Because molten salt operates at high temperatures without requiring high pressure, the risk of explosion is reduced. Passive safety mechanisms allow the reactor to shut down automatically in overheating conditions. These characteristics significantly reduce the probability of catastrophic reactor failure compared to traditional reactor designs. Slide 6. Abundance of thorium resources. Slide content. Thorium 3 to 4 times more abundant than uranium. Major deposits in India, Australia, USA. Long-term fuel sustainability. Reduced supply chain constraints. Thorium's relative abundance in the Earth's crust provides strategic advantage for long-term energy security. Large thorium reserves exist in several countries, particularly India, which has developed nuclear programs specifically designed to utilize thorium fuel cycles. Greater abundance reduces resource scarcity risk and stabilizes long-term pricing structures. Unlike fossil fuels, which are consumed permanently, nuclear fuel cycles can be engineered to maximize energy extraction efficiency. Thorium's distribution across multiple continents reduces dependence on a single geographic location. Slide 7. Safety advantages. Slide content. Lower meltdown probability, passive shutdown capability, lower pressure operations, reduced risk of explosion. Safety considerations remain one of the primary barriers to nuclear energy expansion. Thorium molten salt reactors incorporate passive safety features that rely on physical laws rather than human intervention. In overheating scenarios, the molten salt expands, reducing reaction density and slowing the nuclear reaction. Freeze plug mechanisms allow molten fuel to drain into coolant tanks if temperature thresholds are exceeded. These built-in safety features significantly reduce accident probability and improve public perception of nuclear technology. Slide 8. Nuclear waste comparison. Slide content. Reduced long-lived radioactive waste, lower plutonium production, shorter waste storage duration, improved environmental profile. Nuclear waste management remains one of the most controversial aspects of nuclear energy. Thorium fuel cycles produce fewer long-lived transuranic elements compared to uranium-based reactors. Reduced production of plutonium and minor actinides decrease long-term radiotoxicity. Short-lived waste streams reduce storage time requirements, simplifying geological disposal strategies. Improved waste characteristics may increase political feasibility of nuclear expansion programs. Slide 9. Proliferation resistance. Slide content. Difficult to weaponize fuel products. Uranium-233 contamination challenges. Lower nuclear weapons risks. Enhanced geopolitical stability. Thorium fuel cycles are often considered more resistant to nuclear weapons proliferation. Uranium-233 produced in thorium reactors is typically contaminated with uranium-232, which emits strong gamma radiation. This radiation complicates weapons development and handling. Reduced proliferation risk may allow wider international cooperation in nuclear energy deployment. Technologies that reduce weaponization potential are strategically valuable in maintaining global security balance. Slide 10. Efficiency and performance. Slide content. Higher operating temperatures, improved thermodynamic efficiency, potential industrial heat applications, hydrogen production capability. Thorium molten salt reactors operate at higher temperatures rather than correction. Thorium molten salt reactors operate at higher temperatures than conventional water coolant reactors. Higher temperatures improve thermodynamic efficiency of electricity generation cycles. Industrial processes Industrial processes requiring high temperature heat such as hydrogen production and desalination may benefit from advanced nuclear systems. Expanded applications increase economic values of nuclear infrastructure beyond electricity generation alone. Slide 11. Global research and development. Slide content. China investing in thorium reactors. India developing thorium fuel cycles. US private sector interest. Growing international attention. Multiple nations are invested in thorium nuclear research due to potential strategic advantage. China has demonstrated operational molten salt thorium reactors capable of continuous operation. India's nuclear program introduces in correction. India's nuclear program includes long-term plan to transform towards thorium fuel utilization due to domestic resource availability. Private companies in the United States are exploring advanced reactor designs. Technological leadership in nuclear systems may influence global energy markets. Slide 12. Environmental impact. Slide content. Low carbon emissions, reduced air pollution, supporting climate mitigation, complements renewable energy. Thorium nuclear energy produces minimal greenhouse gas emissions during operation. Compared to coal and natural gas power plants, nuclear systems generate electricity without releasing carbon dioxide into the atmosphere. Integration of nuclear energy with renewable energy sources can improve grid reliability while maintaining environmental sustainability. Stable baseload electricity supply supports electrification of transportation and industrial processes. Slide 13. Challenges and limitations. Slide content. High initial development cost, limited commercial deployment, engineering material challenges, regulatory approval complexity. Despite theoretical advantages, thorium reactors face economic and technical challenges. Development of new nuclear technologies requires significant capital investment. Regulatory approval processes are complex and time consuming due to safety requirements. Material capable of withstanding high temperature molten salt environments may reduce advanced engineering solutions. Commercial adoption depends on demonstrating long term cost competitiveness relative to existing energy technologies. Slide 14. Comparison. Thorium versus uranium. Slide content. Thorium more abundant, uranium more established, thorium potentially safer, uranium currently dominant. Uranium reactors dominate global nuclear infrastructure due to decades of engineering, refinement, and established supply chains. Thorium reactors offer potential advantages in safety, fuel efficiency, and waste characteristics. However, existing uranium infrastructure benefits from regulatory familiarity and industrial standardization. Transitioning to thorium systems would require significant technological investment and policy support. Future of nuclear energy. Slide content. Advanced reactor innovation, integration with renewable energy, role in decarbonization, long-term energy stability. Future energy systems will likely combine multiple generation technologies optimized for reliability and sustainability. Advanced nuclear reactors, including thorium designs, may complement renewable energy sources by providing continuous electricity supply. Decarbonization goals require large-scale deployment of low-emission energy technologies. Thorium reactors may contribute to diversified energy portfolios capable of supporting industrial development and technological progress. Slide number 16. Conclusion. Slide content. Thorium offers promising nuclear pathway, improved safety potential, reduced waste characteristics, strategic energy importance. Thorium nuclear energy represents a technological pathway capable of addressing several structural limitations of traditional nuclear systems. Improved safety characteristics, reduced toxicity waste, and greater fuel abundance position thorium as a potentially valuable component of future global energy systems. Continued research and development will determine whether thorium reactors achieve commercial viability. Energy systems influence economic productivity, geopolitical influence, and technological development, as well as making advanced nuclear technology strategically insignificant. Thank you.